consider the rates of chemical reaction. Say we have a reaction A going to B, and we can plot the concentration of A and the concentration of B. I'll do A in blue and B in red as a function of time. So we'll say at time equals 0, that there's no product B, so it will start at 0, and then B will increase over time, and A, since it's the reactant, starts with a certain value, and it's going to decrease as a function of time. So this is A and B. Now we can define the reaction rate, how fast the reaction is going, by the slope of this curve. And in calculus, we would write the change in the concentration of product B with respect to time is equal to the rate of the reaction, or since A is the reactant and it disappears, then its slope is negative, and so we use a negative sign to make the rate positive. So it doesn't matter whether we express the rate in terms of product or reactant, the rate will be the same. And if we want to approximate the derivatives, we can say, let's look at the rate between 2 points. And this will be delta T, change in the time, and this will be delta A, the change in the concentration of A right here. And so we can express the rate as negative delta concentration of A over delta time. And so this will be an approximation over this time period for the rate of the reaction, where the derivative is the exact instantaneous rate at any point. Now, one thing you'll notice is that as the reaction proceeds, as time gets larger, then the slope decreases in magnitude. So at first the reaction is going fairly quickly, so the increase in B is fairly rapid, but then at long times you can see that the increase of B starts to approach 0. So after A is almost gone, the reaction is slowing down. And you can see the same thing with A. At first the slope for A is large, and then it starts to level off, and the slope becomes less in magnitude. So as A decreases, the reaction rate decreases. So the rate of the reaction changes over time. It's fast at first, and then it slows down as time gets larger. So say we have a balanced equation where A and B are certain stoichiometric coefficients, and A and B are the reactants and P is the products, and you have a balanced equation where A and B and little p are just numbers, just to balance the equation. And if we express the rate of the reaction relative to A, we use a negative sign to make the rate positive since the reactant is disappearing, so dA is negative, so we use a negative sign to make the rate positive. If we express the rate relative to B, if A and B are different numbers, then B's are going to be disappearing at different rates. Say we have this reaction. Hydrogen and oxygen reacting to give water. 2 hydrogens react for every 1 oxygen. So hydrogen is disappearing twice as fast as oxygen is because of these stoichiometric coefficients. And water is being produced twice as fast as oxygen is disappearing because of the 1:2 ratio. But hydrogen and water disappear and appear at the same rate. So we want to be able to have the same rate no matter what we reference it to in the reaction, whether hydrogen, oxygen, or water, or A, B, or P. And so what we do is we divide the rates by the stoichiometric coefficient. So we'll divide by 1 over A and we'll divide by 1 over B for reactants, and we'll divide by 1 over P for the products. Now, I haven't put a negative sign for the rate reference to the product because product is appearing. D concentration of P is positive, and so the rate's positive. So this way, whether I express the rate in terms of A, B, or P, I'll get the same rate because I'm dividing by the stoichiometric coefficient. So in my example here, the rate relative to hydrogen would be equal to minus 1/2 times the derivative of the hydrogen concentration with respect to time. And the rate for oxygen would just be negative 1 over 1. And then the rate for water would be positive 1/2 the concentration of water with respect to time. So I'll just divide through by the stoichiometric coefficient to reference the rate. So now these rates are all the same no matter which species in the reaction I reference it to.